hour. So I'm incredibly excited to introduce Orly Liba, and really during her special day today of presenting and defending her PhD thesis. Orly was the very first person that joined my lab, so this is very much of a very special occasion for me as well, of course, in the most important special occasion for her. Orly, I'm going to keep this short because we've lost a few minutes on the move, but Orly is really one of those people that you can really define as a gross underachiever. And of course, I'm joking, right? So she started out her undergraduate studies in electrical engineering and physics. She wasn't happy with just doing one undergrad, so she had to do two. Now, in parallel to this, she also picked up a very interesting place to work in, which is a place called Rafael in Israel, where she was working also in optoelectronics and developing very, very interesting things for that particular company, which is one of the well-known electro-optical companies in Israel. And so she did that literally in parallel with her studies. It wasn't just like a summer gig or something. It was actually in parallel to that. Then she joined the army and went to one of those special units that no one knows anything about. And it was incredibly high-end developments of, again, electronics, optics, and so on. And in parallel to that, and friends that I've known that have been in that particular unit are telling me that they're spending about anywhere between 100 to 120 hours a week there, and whatever time they've left at home, they do some extra work. She wasn't so much satisfied with just doing that, so in parallel to that, she also did a master's degree and did some pretty sophisticated simulations on carbon nanotubes. So that's another interesting place that she's gone to. As she was doing that and trying to study the basic fundamental physics and understanding that, she finished her army service and then spent a few years in industry. And there were a lot of us grad students have gone to graduate school directly from undergrad. I think there's a very special thing to be said about people that also spend some time in industry first, getting to know what the real world looks out there, and then when they come back to graduate school, they come at it with a very different perspective. And she definitely had a very different perspective. I think if you're looking at the level of maturity that some of us had when we applied into graduate school, in retrospect, I wish I had some more time to spend in industry before I went into grad school myself. And so I was, of course, very, very happy when I got this email from Orly saying, "Hey, heard about your lab from a friend of a friend. Can we talk?" I said, "Of course, by all means." So Orly was really the first person to join the lab. I'm not going to steal her thunder for what she actually worked on, but I think if at the end of this lecture you're not incredibly impressed, I think you've just been sleeping in. So without further ado, Orly.
Thank you for the incredible introduction, and thank you all for coming and for waiting until we sorted out this technical issue. So today I'll present the work I've been doing for 5 years in Adam's lab, and it's computational and optical tools for non-invasive functional imaging with OCT. We will talk about a brief introduction to OCT, contrast-enhanced OCT, speckle-free imaging, and cell tracking in vivo. So first of all, let's think. What would happen if we could see under our skin? A lot of us maybe have some skin lesions and we want to know what's in there. Currently today, if we want to see something, we have to take some tissue out, which is painful, and put it under a microscope in order to see what's going on. Why do we need to do this? Why do we need to take the tissue out and not image it non-invasive? Why do we need to have biopsies? So the question is, why can't we see under our skin? Why do we need to? We know that infrared light can penetrate tissue, but why is it that we can't really see inside it? And the answer is that light is multiply scattered inside tissue. So if I were to take my laser pointer, you see it creates a dot, but if I put my finger, it spreads all over the fingertip. So light scatters in tissue, and that information that's inside the tissue gets drowned in those backscattered and multiply scattered photons. But OCT allows us to see only those backscattered photons because it filters out the multiply scattered photons. It's often explained as optical ultrasound because it images the echoes of light or the reflections in backscattered light. And it's achieved by analyzing the interference of low coherence infrared light. I'm not going to go into too much details about OCT, but with the interference of low coherent light, we can see 2 millimeters inside samples, non-invasively with micron resolution. It's essentially a microscope that can see under our skin. It has intrinsic contrast, so unlike two photon microscopy, we don't need a fluorophore. It images 3D volume with nearly real time. And the main thing about OCT to remember is that the low coherent interference visualizes the reflected photons and rejects the diffuse multiply scattered photons. Our lab uses a spectral domain OCT. So the spectral domain OCT is composed of a broadband source. The light goes from the source to a beam splitter, and then some of the light goes to a mirror, which is called the reference arm, and some of the light travels to the sample, which could be tissue. And then the light reflected from the mirror, the light backscattered from the sample interfere here, and then they're recorded using a spectrometer. So the interference is recorded in the spectral domain. And in order to reconstruct the image, we do a Fourier transform to obtain the image in the spatial domain. The resolution of OCT, the axial resolution is inversely proportional to the spectrum source. So the broader the source, the better the resolution. And the lateral resolution is determined by the lens on the tissue. OCT is usually used in the clinic to see the retina. The retina is the photoreceptors in our eye and the neuron layers. And this is very, very useful in ophthalmology to detect diseases in the eye, such as AMD, because in the retina you can't really take a biopsy. It can also be used in preclinical studies, for example, to image tumor progression and treatment, response to treatment in vivo, because you don't have to take any part of the tissue out, you can monitor it in real time. And these are images from our lab, just to show you the high resolution that we can see in the large volumes that we can obtain in our lab. So this is a mouse pinna, it's like this part of the ear. And you can see the cartilage in the middle, the layers of the skin, blood vessels, and lymph vessels. However, conventional OCT provides only structural and anatomical information. It does not show anything functional or molecular information. So now we go on to molecular imaging. And I want to give you a brief introduction to molecular imaging and why it's important. Say we want to image molecules, for example, cancer biomarkers attached to a cell membrane. This might be important to understand what cancer is in the tissue, and also to understand what happens when we treat cancer before the tissue shrinks. But proteins are small, and we can't really visualize them with conventional methods. So what we do to visualize them is attach a beacon with an antibody, for example, to see the molecules indirectly. And the beacon provides a new contrast mechanism. So there are various in vivo molecular imaging modalities, as you can see here, function of resolution versus depth. Optical microscopy has very high resolution and shallow depth, and MRI and PET have a very high depth but low resolution. And our lab is bridging this gap by using OCT to enable in vivo molecular imaging with single cell resolution at a depth of a few millimeters. So we developed contrast-enhanced OCT, which is a new contrast mechanism to visualize biological processes in addition to structure. First of all, we had to find a contrast agent for OCT. And the problem is that OCT signal of tissue is very high because tissue itself backscatters a lot of light. So which contrast agent will provide a detectable signal? And our approach was to use metallic nanoparticles because they have a unique scattering spectrum. For example, gold nanorods, which are also good to use because they're made out of gold, which is inert, are like tiny antennas. And being tiny antennas, they have a little resonance. So they have a very unique spectrum which we can detect. But regular, conventional, small gold nanorods don't have enough scattering signal. So Elliot in our lab developed and functionalized large gold nanorods. And these large gold nanorods have increased backscattering compared to the conventional gold nanorods, and also have a better spectral signal. So here we see the mouse pinna again, but with a tumor. So this is the tumor, it's a cross-section of the pinna, we see the layers of the skin and the tumor. This is before the injection, and the injection of the gold nanorods is done to the blood vessels of the mouse. After the injection, this is what we see. So we see a little bit of increased signal in the blood vessels and deeper vessels inside of the tumor. But overall, the signal is not enough. The LGNR signal to background ratio is still insufficient. And that's because we haven't used their unique spectrum yet, only their increased scatter. So let's see how we can use their unique spectrum. And we do that by spectral analysis. So OCT raw spectral signal, which is the interferogram that we record, encodes both the location of the scatterers and the scattering spectrum, as you can see here. And that's the interferogram, which we do a Fourier transform to get the image. In order to image the gold nanorods with this spectral peak, which is unique to them, we reconstruct the interferogram with two bands. So we call this the dual band method. And the image constructed by band 2, which has the peak of the gold nanorods, will have a higher signal in the location of the gold nanorods. That's the basic principle. Now we take the two bands, we reconstruct the images and subtract them. But this isn't a very reliable signal. You see the image, we get two misaligned images here. The misalignment is due to dispersion because of the dependence of the refractive index on lambda, the wavelength. So we had to fix dispersion in order to get a reliable spectral signal. And that is done by adding a phase that is linear with lambda during the reconstruction. The phase is found iteratively to minimize the difference between the shifted images. So we basically use spectral analysis to correct for dispersion. Okay. This is the image before and after correcting dispersion. But this still isn't a reliable spectral image. We see that there is a depth dependence inside of the tissue. Why is there depth dependence? Well, there are several factors in OCT that are spectrally depth dependent. The most dominant is chromatic aberration, which is caused due to the lens not focusing all the wavelengths at the same spot. So in order to fix that, we implemented a depth-dependent spectral gain, which is calculated to compensate for the chromatic aberration. The gain is calculated automatically, assuming the spectral neutrality of the tissue. So everything is done adaptively and automatically. We don't have to guess where the focal plane is. After dispersion compensation and the chromatic aberration correction, we finally have a reliable spectral signal in the blood vessels. So you can see that the signal in the blood vessels has a high spectral contrast. However, please also notice that there is speckle noise in the static tissue. And that's the second part of my work that I will discuss a little bit later. In addition to spectral contrast, we also detect flow. Flow is detected by speckle variance, the signal fluctuation owing to blood vessels. Okay, so let's see what we get now. These are the images I showed you before, pre-injection and post-injection. When we add spectral contrast and flow detection, now we can really see a difference, a large difference in the blood vessels after we inject the gold nanorods. We measured the sensitivity of our detection mechanism ex vivo, and we see a 50 picomolar sensitivity in blood ex vivo. These are capillary tubes filled with increasing amounts of LGNRs. In order to measure the sensitivity in vivo, we did incremental injections intravenously to a mouse. So with increasing injections, we get, and measuring the signal in the blood vessels, we measure a 250 picomolar sensitivity in vivo, which corresponds to only 40 nanoparticles per voxel. And this is unprecedented in other in vivo molecular imaging modalities. Next, we wanted to see if we can detect multiple contrast agents. So the LGNRs, because they're like tiny antennas, their resonance can be tuned by changing their aspect ratio. It can be shown here. And we are able to differentiate between them also based on the spectral contrast. So here we have two types of LGNRs. And the spectral contrast algorithm can separate the 815 nanometer LGNRs and the 925 nanometer LGNRs. We demonstrated multiplexing by injecting the LGNRs sequentially at adjacent sites on the ear pinna. This image shows us the blood vessels of the ear pinna. Now we inject the 815 LGNR subcutaneously, and we see them drain through a network of lymphatic vessels. Now we inject the second type of LGNRs to a different site, and we see another network of LGNRs. So we simultaneously see two types of LGNRs inside of the tissue and enable multiplexing. This gives us high-resolution mapping of actively draining lymph vessels and a platform for studying lymphatic clearance. Another thing we can see, if we look even closer, is we can see the structure of the lymphatic vessel. So lymph vessels are made out of segments called lymphangions, which have valves to regulate unidirectional flow. In this image, we can see the LGNRs, and the lobe structure are the lymphangions and the valves. Here we see like a dead end. This shows a valve that doesn't let the LGNRs downflow. Now we inject a different kind of LGNRs. We can see that the 925 LGNRs can flow downwards, and the 815 LGNRs and this valve prevents the 925 backflow here, but lets the green LGNRs flow in the correct direction. So we really can see the functional states of the valves and understand the lymphatic flow using these types of experiments. To summarize this part of the project, we developed a platform for molecular in vivo imaging with OCT. We call this platform Mozart. It enables 4-micron resolution, 1 to 2 millimeters of depth. We developed a contrast agent, LGNRs. We have 50 picomolar sensitivity ex vivo and 250 picomolar in vivo. We can detect multiple contrast agents, and we can gain biological insights, such as enhanced imaging of tumor microvasculature and mapping lymphatic drainage. We have both structure and function, which weren't enabled in OCT previously. Okay, so now let's tackle the next issue with molecular imaging, and that is, what about the speckle in the static tissue? It basically prevents us from seeing the LGNRs in static tissue, and one of our goals is to see them bound to targets. So we have to fix that. But speckle noise doesn't only prevent spectral contrast to be reliable, it also affects the visibility of the image. So speckle noise is caused by the coherent interference of OCT, and it looks like salt and pepper noise. You see, this OCT image is not as detailed as this H&E stained histology. A lot of the structures are hidden because of the salt and pepper speckle noise. Speckle noise is caused by interference of multiply scattered light. So light that travels to the tissue gets multiply scattered in the voxel or multiply scattered by other scatters on the way. And it causes destructive and constructive interference, which cause black and white noise. And we definitely want to solve the issue of speckle noise without reducing resolution in order to enable molecular OCT, molecular imaging OCT, but also to increase the visibility of OCT in general. So the issue is with speckle noise because it comes from within the tissue. If the tissue is static, it won't change in time. So we can't average it out in time, unlike other types of noises. So what do? We notice that inside of the blood vessel and under it, the speckle does change because of the flow and is averaged out. Okay, that was our big insight. Our big insight was that if we can change the speckles in time, we can remove them without compromising resolution. So what we wanted to do is mimic the effect of the blood vessel in order to get the speckles to change in time. How do we do that? Our approach to do this was to scramble the phase of the incoming light to the sample. So let's look at this a little bit closer. We have two particles inside of the voxel, and the light coming back from them interferes to cause a dark speckle. But if we scramble the incoming light and change the phase incoming to these two particles, we can modulate the speckle pattern, and by averaging it out, we can remove the speckle noise. We call this method speckle modulating OCT. We implemented this by moving the diffuser in the focal plane of the original OCT. And we relay the focal plane of the OCT using 4F, two lenses in a 4F configuration. This is how the setup looks in real life. So the original probe of the OCT is composed of this and this. That's the diffuser in a rotating mount. We have the two lenses to relay the focal plane, and we also have an extension to the reference arm because of the extension to the sample arm. As a first demonstration, we wanted to see how much we can increase the visibility with SMOCT using a phantom composed of LGNRs and agarose gel with 3-micron beads embedded inside it. We have here conventional OCT and speckle modulating OCT with 5 averages, n is the number of averages. We see speckle in the OCT. We start to see the speckle being removed in SMOCT even after 5 averages, but we still see a lot of noise. Let's increase the number of averages. The OCT image stays basically the same because the agarose and the gold nanorods are static, so the speckle noise doesn't average out. We start seeing a little bit more here. When we increase the number of averages further, we can really see the embedded beads inside of the phantom. Okay? So we can really appreciate how much SMOCT increases the visibility inside scattering media. We also looked at the speckle statistics. So speckle statistics have very well-known characteristics of a Rayleigh distribution. This is the distribution of the signal inside of the phantom. This phantom has gold nanospheres and agarose. When we increase the number of averages in OCT, as we expect, the distribution of pixel values does not change. But in SMOCT, the distribution becomes much narrower as we increase the number of averages. It stops being a Rayleigh distribution and it becomes a Gaussian Poisson distribution. And this distribution basically describes the randomness of how many gold nanospheres are in a voxel. Okay, so we understand that we're removing speckle also by the statistics of it. There's another theoretical, another theorem that we wanted to show that to prove that we remove speckle as expected, and that is by looking at the speckle contrast as a function of number of averaged frames. The speckle contrast is defined as the standard deviation normalized by the intensity, and by theory we know that it's supposed to decrease as 1 over the square root of the number of averaged frames. And we see that when we measure the speckle contrast in our phantoms, the normalized speckled noise does decrease as expected. We also measured the effective resolution increase, and we see that we, by measuring a gap in a phantom, a PDMS titanium dioxide phantom, and we see that the gap, and we measure when does the gap disappear. By measuring where does the gap disappear, we can measure the effective resolution. And we can see that by comparing the OCT and SMOCT to measuring the gap with a microscope, that the effective resolution increases by 2.5. Okay, now we can start looking at demonstrations in vivo. This is the mouse ear pinna with speckle and with speckle modulating OCT. When we zoom in, we can really see these tiny structures in the mouse's pinna and the hair follicles, and we're starting to get closer to an in vivo biopsy. We can also segment some features owing to this increased visibility. So this movie shows how we can segment features and understand where they are in 3 dimensions. We also looked at a mouse cornea in vivo. The cornea is this part of the eye, the front of the eye. It looks like this when you do it in histology, but in regular OCT, you don't see these structures very well. You see the layers. When we apply SMOCT, we can really see the cellular structures in the cornea by removing the speckle noise. We also looked at a human fingertip in vivo, of course, without taking any tissue out. we can see the sweat ducts and nerve bundles, which are called tactile corpuscles. It really starts to look like an in vivo biopsy because we can see more structures with speckle removal. Next, we wanted to look into the brain of mice in vivo. So Derek in our lab was able to implant cranial windows into mice in order for us to be able to look inside them. We adapted the SMOCT system to a new wavelength at 1300 nanometers. But the system is basically the same with a glass diffuser, which is moving or rotating, and a 4F lenses configuration. We look at the brain from top to bottom axial direction. This is conventional OCT. So we see the two hemispheres. This is the sagittal sinus, some veins. If we don't see a lot of structure, we see a lot of speckle. When we look at SMOCT, a lot of the speckle is gone. And as we get closer to the focal plane, we can see white matter structures. Those fibers are white matter fascicles. This is the zoom of the cingulum bundle. The cingulum bundle is like a highway of the brain. And to our knowledge, this is the highest resolution, high field of view, white matter imaging seen in live animals. We can also enhance these images. So in this image, we removed the shadow of the blood vessels. We also denoised the images with an anisotropic diffusion denoising and also light contrast enhancement. So now we can see the fiber structures much better and kind of imagine how they connect in the brain. We also looked at mouse brain tumors in order to show how we can see the tumor margin. So here we have a tumor. This is the top view, sagittal view, which is the side, and a front view, which is the coronal. You can see the tumor here, but this has speckle in it. When we remove speckle, we can see the tumor margin much better at a close to cellular resolution. We were also able to obtain samples from humans ex vivo of a low-grade glioma. So low-grade glioma is a cancer that, when removed completely, can increase the survival rates of patients to 97%. So it's really important to have complete resection of these tumors. This is a histology of tumor and regular tissue. So we can see where the tumor is by looking at the density of the nuclei inside of the tissue. And we can kind of estimate the tumor margin is kind of here. When we look at this sample in OCT, we see, this is SMOCT, we see a small difference in signal intensity. The signal intensity difference is because the myelinated structures inside of the healthy brain reflect more light. When we increase the contrast, we can clearly see the difference in signal values, and we can also kind of estimate where the tumor margin is. Now, this could have very big implications in the surgical context. We can also see the tumor margin by looking at layer 1 of the cortex. So this is a top view. This was a side view of the brain sample, but this is a top view. So here we have a top view, we see the blood vessels. And layer 1 of the brain has axons that we're able to visualize only thanks to SMOCT. And you can see that here the axons kind of stop. So it gives us another way to look at the tumor margin in vivo. Well, this isn't an in vivo, but imagine taking this SMOCT and taking it, applying it to the surgery. So SMOCT can help surgeons remove brain tumors during surgery. With a complete resection, we would get increased survival and preserve healthy regions of the brain. As a mid-summary, another mid-summary, we have SMOCT, a platform for unlimited speckle removal. It uses phase scrambling to obtain unlimited speckle patterns. We saw that the statistics change from Rayleigh to Gauss, and that the effective resolution increases by 2.5. I saw that Audrey.
Yeah, so she should be able to hear you out of this. Check, ask her if she can hear you.
Can you hear me, Audrey? Can you hear me?
Yes, I can hear you. What slide are you on?
Oh, I'm sorry.
56.
Slide 56. Okay, so we are able to increase the effective resolution by 2.5. We implemented SMOCT on two systems with 900 nanometers and 1300 nanometers, and we can reveal fine structures in vivo: mouse pinna, cornea, and brain, and a human fingertip. We can also enable this type of work may enable studying mouse neuroscience in vivo and could improve surgical outcomes by detecting tumor margins. And now we move to the last section in the talk, which is combining speckle removal with detection of the contrast agent to approach molecular imaging with OCT. I'll also show you briefly a method to detect the contrast agent in tissue ex vivo based on machine learning. So as I just said, we're going to combine looking at the mouse's brain with SMOCT at this wavelength and the use of gold nanorods and spectral analysis. We inject the gold nanorods intravenously to the mouse, and the mouse has a tumor in its brain. We can look at the brain through a cranial window. Before injection into the brain, we can see the tumor has a relatively neutral spectral signal. It doesn't have the large gold nanorods inside it. After injection of the LGNRs, we see the blood vessels inside of the tumor light up with the spectral contrast. 40 hours after the injection, when all of the LGNRs cleared out of circulation, we see that in the tumors, there are several regions which still may have LGNRs in them. But we still don't know where the LGNRs are accumulating. We can see them in the brain, but we don't know really where they are. So even before this project, our lab has developed a method to detect the LGNRs in tissue sections. And why is that a challenge? So LGNRs can't be seen with bright field imaging. They're just, their signal is much lower than the signal of the rest of the images. But we can see them as bright spots with dark field imaging because they backscatter more light than the tissue itself. When we use hyperspectral imaging, we can see them even better because we can detect them owing to their unique spectrum. We call this HSMAD, hyperspectral dark field microscopy with adaptive detection. And in this publication, we showed it for several nanoparticles and to demonstrate how we can calculate the biodistribution inside of tissue using HSMAD. It's based on detection using k-means. So k-means is an unsupervised training method. It's an iterative clustering algorithm in which each observation belongs to the cluster with the nearest mean. We use it to calculate 4 spectral cluster centers. So these are calculated automatically, but they also correspond to the expected physical spectra in the sample. Eosine is part of the HNE dyes. So eosine and hematoxylin, which were calculated automatically, are the dyes inside of the HNE stained tissue. The LGNR cluster is also detected automatically, and we have another intermediate cluster, which is a mix of the previous three. We encountered chromatic aberrations, so we manually added a 5th cluster to reduce false positives, because it looks a little bit like the LGNR cluster. Classification is done by Euclidean neighbors. So each pixel spectrum is compared to the cluster centers, and pixels that are closest to LGNR cluster are classified as LGNRs. Now we go back to looking into the brain and finding where do these LGNRs accumulate inside the tissue. We look at the hyperspectral bright field microscope of brain, non-tumor, and tumor. So first of all, we can see that in the brain, the LGNRs are not detected. So the LGNRs are only inside of the tumors, you can see here.
We also combine bright field imaging. So these are the same sections with bright field imaging, but in addition to that, we have HRP staining for CD68. So CD68 is a marker for macrophages. So essentially, it's that where we have dark areas showing HRP is where we have CD68 and possibly macrophages. When we register the two types of images together, the bright field and the dark field images, we have over 50% co-localization of LGNRs with the cells expressing macrophage biomarkers. So we can conclude that the LGNRs are in tumor macrophages. So this suggests a method for labeling and tracking cells, the macrophages, in vivo, as you can see here. After the injection and the clearance, the LGNRs perform EPR in the tumor. EPR is enhanced permeability and retention in the tumor, and then they get taken up by the macrophages of the tumor. So this is a movie showing the volume of the brain and the tumor, and the macrophages tracked through time. So that's the regular. Oops. I wonder if I can pause this. Okay, I'll just stop quickly. This is the brain volume top view. Now we detect the blood vessels and register them with regular OCT. We zoom into the brain tumor. The LGNR clusters are segmented by spectral contrast and the SMOCT signal, so a combination of them is used to segment them. And the colors encode different time points. So what we see is that we can track the macrophages labeled by LGNRs in vivo in almost real time. Here is another time sequence. Now we zoom out to see the tumor in the brain context. Okay. To summarize, we have shown how LGNRs can be detected with high resolution and sensitivity using adaptive spectral analysis algorithms. SMOCT brings us a step closer to enabling non-invasive biopsies and has the potential to assist in surgeries. Spectral reduction combined with spectral detection of contrast agents can be used to track cells inside living tissue. These are the main publications for the work presented here. All of the code is on GitHub. I want to touch on a few possible future directions. So in terms of capabilities, once we have the ability to scramble the phase inside of the voxel, perhaps we can create some super resolution with SMOCT to see in higher resolution inside of the voxel. So this is a direction that we started exploring. Also increase the accuracy of spectral analysis to enable higher multiplexing, and also to create a contrast agent at higher wavelengths. In terms of applications, future directions could be cell tracking, for example, for studying circulating tumor cells, CTCs, and immunotherapy. And also diagnostic and intraoperative SMOCT, because it gets us closer to biopsies. These are the publications that I contributed to, and now I would like to thank my colleagues, collaborators, mentors, and the lab's funding. Especially, I want to thank Adam de la Zerda, my advisor, Steve Chu, who's been a collaborator on the SMOCT project, Elliot, who co-authored almost all of the papers with me. He created the LGNRs and did a lot of the biological work. And Derek, who's a neurosurgeon in our lab, who also did a lot of the biological work and the cranial windows. Thank you very much, and I'll be happy to take questions.
Could you check that she's still there?
Audrey, are you here? Audrey?
Yes, I'm here. If you could just repeat
Sure. Any questions? Yes.
To the brain, how deep?
The question was how deep can we see inside of the brain? I think we showed about 1 millimeter deep, but we can see down to 2 millimeters deep. The focal depth of field is not very large. So, and also we lose a lot of signal at the bottom. So it doesn't make sense to show more than 1 millimeter. Yes.
Thanks for a great talk. What's the limiting factor on temporal resolution? And is there hope at getting faster in the future?
The question was, what is the limit on temporal resolution? OCTs are getting very, very fast. So there are OCTs that can do 1 megahertz A scans. Those are the most state-of-the-art. The limiting factor is how much light you want to capture. So you have to have very sensitive spectrometers to capture the light. I think that's the major limitation. There are also swept source OCTs that have a sweeping OCT and can use a simpler detector. I think those are the fastest, but then you need enough light to go. You need to have enough intensity to shine on your samples for that. Yes.
That was fantastic. How do you envision that a device like this might actually be used during surgery simply?
Oh, okay. The question was, how can it be used during surgery? So this question is actually very close to what we're planning to do. So Derek, that's sitting right behind you, he plans on integrating OCT into the surgical microscope that are being used in neurosurgery. And once you do that, it's basically you can switch between them and see in addition to the surface of the tissue inside of the tissue. And SMOCT, as you saw, is it's not too complicated to implement. So you can adapt. You can include it as an adapter to any OCT.
So more practically, would it be the surgeon would scrape out a little tumor and then see, did I get it all by using your device and seeing what's just under the surface?
They can either look on the tissue after they took out the tumor, or look at the tumor margins at a separate station in real time. Instead of doing all of the H&E staining, which takes hours, they could just do it with OCT in real time. There's actually a company called Synaptum that does those benches for surgical purposes. Thanks. Any more questions? Yes.
This is for the contrast agent. Since the tissue is already really scary, as you mentioned, have you considered doing like a negative contrast, nanorods or anything like that, which is very homogeneous and not standard?
Yeah, so the question was if we considered negative contrast agents. We considered that in the beginning, in the very, very beginning, but we imagined that they would make shadows as well. So I think they're less preferred, but we consider those at the beginning as well. More questions? Okay, so I have a lot of acknowledgements. That's okay. Okay, so I really want to thank my committee. Adam, you've been a great advisor. You taught me so much about research, publishing, and life in general. Steve Chu, I love collaborating on the SMOCT project with you and your team. It's always fun to talk with you both about politics and physics. Audrey, I'm really sorry you can't be here. You and your lab played a huge role at the beginning of our lab and taught us a lot about OCT and making phantoms, especially Jenna, who's over there in the back. I had the pleasure to assist you in an optics class in summer school, and I enjoyed working with you. Gordon Wetstein, TA in computational imaging and display was one of the best experiences for me at Stanford, so thank you. I've enjoyed interacting with you and your lab members and brainstorming new ideas. Sandy and Phil, thank you so much for agreeing to be my chair. I know you mainly work on CT and MRI, and perhaps one day OCT will also become as clinically relevant. Now, I wanted to thank the Lazerda Labs. I think everyone is included here except for unfortunately for Lily and Saba, who are new in the lab. The lab has been my second home for 5 years, so thank you for being such good friends. I feel we've built something great, and I'm sure you guys will continue to discover new ways of pushing the boundaries of medical imaging. A lot of photos here, I know. Next, I want to thank the women of electrical engineering. Thank you to those who came. You've been great friends and created lots of opportunities for socializing and developing academically and professionally. I want to thank the Stanford Optical Society. It's a group of brilliant scientists. It's been fun learning about all kinds of stuff related to photonics and light with you. My Ignite team, so we actually tried to create a company using SMOCT called Free Diopsy for seeing under the skin, and it was a great experience. A lot of thank you to BioX and Haida. Thank you so much for your help today. It's an awesome community and a platform for collaboration, enrichment, through poster sessions, symposium, and professor lunches. I'm incredibly fortunate to be a part of BioX, and also we got some cool swag. I want to thank my many friends at Stanford in structural biology, MIPS, the EE department, and in Escondido Village. Dor and I, Dor, thanks for coming. We studied through calls together. I won't forget that time. Tanya, thanks for being a good friend in general. And of course, I want to thank my family in Israel, my parents, in-laws, and siblings who've been cheering for me 5 years from Israel. My 2 kids, Oshik and Ella. Thank you for putting things into perspective and reminding me what's important. And last but not least, Itai, thank you so much. Thanks for joining me on this adventure. You're a wonderful father, spouse, and hacker. That's him in his natural state. Always happy to help and the most generous person I know. So thank you so much for coming. These are all the acknowledgements. And closed session.
All right. Now
Let's
it's time
take a
to
5-minute break and reconvene. 5 minutes.